So this is Mark Chen, and our next speaker is Justin Cao, and he will be talking about the lightweight face detection method we working on the Himax ultra low power WEI plus AI processor. And Justin is a master student of electrical engineer in National Cheng Kung University in Taiwan, and his major is research is in the machine learning, in particular, field shot learning and deployment development on edge devices, and lead by Professor Minder Xie. Justin and the lab members have accomplished quite a few innovative research projects together with Himax. So the floor is yours, Justin.
Okay. Hi. Okay. Thank you, Mark, and thank you for your introduction. And I think it's my pleasure to have a chance to share with you at a TinyML and as a student. So today, my presentation talk is related to our project that we recently cooperated with Himax Technology, and it's a lightweight face detection method working with the Himax ultra low power W1 plus AI processor. So for edge devices, their test is to operate under the premise of power saving. But running a powerful algorithm all day long is unnecessary, and because it consumes a lot of energy and causing poor battery life. So we adapt the concept of low power always on sensing. And we want to develop a smart algorithm, and we want it can act as a guardian to keep watch. The methodology we propose is to develop a lightweight face detection algorithm that can detect if anyone approach and wake up the complex algorithm only when someone is nearby. The difficulty of this whole thing is due to the hardware limitation of edge devices. We cannot directly apply common algorithm to reach our goal. So the next slide, we will introduce how we can achieve our goals with a limited resource, and we want how we optimize we have done. So let's introduce the target platform first, the W1 Plus by Himax. Our following algorithm details are based on the platform, and the W1 Plus AI processor is a compact platform for edge devices. It has an ARC EN90 DSP by Synopsys on board, and its system coverage is up to 400 megahertz. And the range size available is 256 KB DCCN for model parameters and input rate, and 232 KB XCCN and YCCN we use for storing intermediate picture map during inference. It also comes with a camera with 640 by 480 resolution that we use to capture frames for proposed face detect algorithm. So here's the big picture. Remember the hardware limitation we mentioned before. The range size is not big enough, which makes it impossible to do single-shot detection like YOLO or SSD on the whole frame. Therefore, we adapt the idea of sliding window and the image pyramid to accomplish face detection on the entire image. This means we should resize the input image into multiple sizes to form an image pyramid. Then for each scale image, we use sliding window to go through every position of the image and crop out several small windows to examine if it is a face or not, one by one. And this page is to discuss our target in detail. And our given target is to detect faces in between 1 meter and 4 meters. According to our experience, the face that is far away is the most difficult to detect because of its size is too small and with this feature. So it will be a difficult part in this problem. And by our measurement, we noticed that the smallest faces, which is in the distance of 4 meters, is about the size of 25 by 25 pixels. This will largely determine the input size of our face detect model. And now we know the exact problem we are facing. And I want to introduce some related work that can help solving our problem. The FDCNN is an efficient and a lightweight model for face detection problem. And they also adapt the setting window and the image pyramid method to solve the face detect problem, which is similar to our solution. Nevertheless, it can also locate facial parts at the same time. It only takes 100,000 of parameters for the model, but it still can get an impressive score on FDDB face detect benchmark. However, along with the complex model structure, its intermediate feature mask size is too large, that make it impossible to fit in the limited memory size on our platform. And you can see the feature mask size after the first convolution is way too big for our memory size. I mean the XCCN and YCCN. So we redesigned the FDCNN to derive a lighter model, denoted as a RFDCNN, which means the hardware limitation mainly by reducing the input size of a model to 24 by 24 pixels, with some other adjustment like downsize the feature map with the pooling layer. Our model is much lighter and faster compared to a reference FDCNN. Our FDCNN uses about 45,000 parameters, which is 57% less than FDCNN. And by calculation, our model speed is 4 times faster compared to FDCNN. This makes us can accomplish our mission more efficiently, and we also prove our model is still accuracy in a later experiment. Okay. In addition, we further make good use of the cascade architecture from well-known face detector, the MDCNN, to reduce the overall time complexity. And the idea of the cascade architecture is to use a smaller proportional net in advance to filter out simple negative windows, and only leave the difficult windows to the following up bigger models, because bigger models make accurate prediction. And such architecture can prevent using big model even when facing easy cases. And to minimize the computation, PNet from MDCNN set its input size to 12 by 12 pixels and use only 3 convolution layers. And this simplifications effectively reduce the calculation time of a single window to less than 1 millisecond. And it's 0.57 millisecond here. And suppose we use the PNet as a pre-processing model. In the case that a window can save us 12 milliseconds, and an improvement has a total of 1,000 windows to be tested. Ideally, most of the windows will be shared, and we can save more than 10 seconds of computing time, which will be a very amazing improvement. So for the flow diagram of MDCNN here, you can see the stage 1 and the stage 2 model filter out most of the negative window, and this is why MDCNN is so fast. So here's a completed system framework. Overall speaking, both models are implemented in our system. So we first use a sliding window and the image pyramid to exhaustively crop out the improvement into candidates. So, and then we use the PNet for stage 1 model to filter out most of the unlikely candidates fast. And leave few candidates who may be fast for later prediction. And the rest of the candidates are sent to the stage 2 model RFDCNN for more precisely prediction for phase or non-phase. After all the prediction, we can know if there are any phases in the improvement and their precision as well. This cascade strategy could make our system more accurate and efficient. So to evaluate our face detecting system, the RFDCNN with PNet is tested on the FTDB benchmark 2. The model has promising performance on face with its minor axis is larger than 25 pixels, but it is good. And 0.9 TPR rate means we can deal with most of the faces in the real life using our model. Although our performance is this impressive compared to NTCNN, but it is good enough for solving our problem. We choose the TPR rate at 2000 false positive, which is a loser condition. This is because in our application, we can sacrifice some precision rate in exchange for higher accuracy. And there are test images from FTDB here. And our system to catch most of the faces in the test case. And I want to introduce some notation first. And the green and the red circles are ground truths labeled by the benchmark. And the green ones are faces with its minor axis bigger than 25 pixels, and we can call it a big face. And the red ones are for faces with minor axis smaller than 25 pixels, and it's a small face by our definition. And the blue, the rectangle is the prediction given by our face detection algorithm. So because of the differences of shape, so we use the intersection over union, or you can say the IOU, to determine if it is a successful detect or not. And this example covers some worth discussing points. And in this image, some audience in the background are also detected. Their faces are blurred because they are off focus, but this does not affect our algorithm. And in this image, some faces are partially occlusion, or only half of the face remain, like this one. But this does not cause any impact because our algorithm is just like humans. As long as there are some features that allow us to judge, even if half of the face is missing, we can still recognize it as a human face. And I don't know if you can see, there's a small detecting box here. And sometimes our algorithms think of certain facial features are complete faces, but I don't think this is an actual big problem because it's still a face here. And this one is a very interesting case. There are several photos in this image, and all of them are correctly detected. This is not surprising after all, and there is not much differences between the face in the photo and the normal one. And the next one, the lady on the left, and the next one picture here, the lady on the left was only photographed on the side face because our model proved that it is capable to detect it too. So the overall say, our model does perform well on FTDB benchmark. Faces of all races, skin colors, and edges, or even different head angles can be detected. And to evaluate our system under more realistic scenarios, we create a data set of our own. So we call it a HiMax benchmark. The HiMax benchmark consists of 6,000 images captured by camera on WM+. It contains several realistic non-ideal and non-ideal scenarios, including face with accessories and environment illuminance, which means the face is in very dark or very bright environment. And facial expression, which is someone making face or in other expression. And different head angles, including head pitch and the head yaw. The head pitch is your head goes up and down, and the head yaw is the face. You are not facing the camera, so the camera can only capture your side head. And the most tricky one is a high noise case. There is faces that someone in very dark environment. Then the camera will receive a lot of noise and cause highly misleading to the model. And you can see the TPR here is dropped a lot. And this is still a big problem, not only for our algorithm, but for most of the facilitators. And another case is the backlight. Backlight is another problem because the high brightness contrast will cause more false precision around the human body. And detecting multi-phase in an image is not a big problem for us. And since our algorithm is designed to find faces in every position, so the numbers is not a problem. And under most scenarios, our system performs well, including some critical cases like face with mask, and which is a common situation during the COVID-19 pandemic. So we think it's very suitable for real-life application. And there's something interesting. And in our head pitch test, we use a dummy head for taking photos, and our model thinks it's a phase 2. And this could be a problem, but it depends on the usage of a scenario in practical. And this chart is to show how we allocate data on W1 plus in practical. And so first of all, to meet the hardware limitation, we quantize all the parameters to the INT16. All of the model's parameters and the candidate windows are stored in the DCCN. And the intermediate feature maps due to inference are stored in the XCCN and the YCCN and passed with the ping pong mode. So at the beginning, we move one of the candidates from DCCN to the XCCN for the first inference. And then the window is passed down all the way through the flowchart. This flow will be repeated until all candidates are predicted. And the range numbers about the block are manually used in each stage. For example, the 23K byte is from the feature map size with the 22 by 22 by 24, and the 24 is referred to the channel numbers. So for 2 bytes each, there are 23K bytes matching the above number, and it's basically the size of the feature map. With the flowchart, we notice that the memory peak happened after the first convolution layer, and it's this one, which is about 23K bytes on XCCN. But it's still within the limitation of XCCN memory size, which made it possible to run on the platform. And then we analyze the timing of our system with EMB Arc MLI library first. And windows are downsized for PNAND since its input size is half the size of RBCNN layers. The equivalent input size is 320 by 240 for PNAND. Then resize for 4 scales, which are 1 and 1.5, 2 and 4 respectively. Here's a little demo for the scale factors. Since our window size is fixed to 12 for PNAND and 24 for RBCNN, the problem is if the face is too big, then the window will only cover part of the face, and this will cause some misjudgment. So we use the scale factor to resize the whole image. After resize, as you can see, the face is smaller, and now we can detect it with the specific window size. So let's back to our project subject. Our algorithm covers a wide range of face size using different scale factors. That is, the scale 1 is designed to detect faces 4 meters away, which is about 24 by 24 pixels. The scale 1.5 is designed to detect faces 3 meters away, which is about 32 by 32 pixels. The scale 2 is designed to detect faces 2 meters away, and which is about 48 by 48 pixels. And the first scale, and the scale 4 is designed to detect faces 1 meters away, which is about 96 by 96 pixels. And the first scale is set with the face size limited of our detection system. This means scale 1 is for detecting the smallest possible face with a size of 24 pixels. So with the 12 pixels per strike, there are about 856 windows in total, which cost 500 milliseconds to inference. The P9 average filtered out 50 windows in high-max benchmark for RFT-CNN to inference. And the inference time then with RFT-CNN costs about 600 milliseconds. So in summary, our system costs about 1 second per frame, which satisfies one FPS requirement for AI doorbell. And we also implement our system with TF-Lite framework. The TF-Lite quantizes the parameter into INT8. It is 1 byte for every parameter. And automatically arrange the hardware usage, including the memory cells. So with TF-Lite framework, inference a window costs 4.8 milliseconds compared to the 12.8 milliseconds with EMB MI library through our manual implement. This is a big improvement, and we will boost up our overall computation efficiency. So in conclusion, we designed a lightweight face detecting system to satisfy the requirement of low power always-on edge devices. And we think with this system, the whole procedure will be more efficient. Our product can be used for several applications. For example, we can place it on the door of a vehicle of your home to pre-record when someone's suspicious approach. And our always-on sensing feature can reduce the misjudgment caused by non-human movement and reduce the power waste of false pre-recording. And another example is to use the proposed algorithm as part of the face recognition system to alert the system when faces show up and also report the face position at the same time. Or we can also place our system in a public place to calculate the flow of people. This is a very critical application during the COVID-19 pandemic because we will need to monitor the condition of people in a place. So we hope this system can be applied on more devices to fulfill the vision of smart home. Okay, so here's my presentation. Thank you for your attention.
Okay, thanks, Justin. It's a very fantastic talk. And I have some question for you. One is from our audience, Light. He just asked about, because you just mentioned your face detection can work on the different light condition. So he just want to know that, do you need any pre-processing, just like an ISP to do the image processing to solve the light condition issue? For example, backlight or some extreme light condition. Do you need that, or you just use the model to do this?
Okay. So this problem is about the noise, and how about using a preprocessing to deal with the noises. And we do use some preprocessing method like denoising with the Gaussian blur or something. But we noticed that with the Gaussian blur or other way to do denoise, it will make the model performs worse. So our solution now is to let the models to deal with all the non-ideal cases. And because with our experiment, the preprocessing sometimes made the model performs worse.
Okay, great. So the other question is that from your eyes, that do you training your model with the color image or just with the mono image? Because we know that the data size and will be very different.
Yes, we train the model with the grayscale image because the camera on W1 only give us the grayscale. So for the model, we train it in a grayscale mode. Yes, that's it.
Okay. Great. So, is there any impact if we want to detect, just like your slide, previous slide, you can detect many faces in the same frame. So, if we want to different more than one faces, is there any impact to the inference time? I mean, the frame rate will be lower.
They in more faces in the window means there may be more candidates, so it will be slightly impact the overall computation time. But I think it is not a big problem because our models go use sliding window method to examine all the small windows. So the overall computation time will be increased, but not a very big margin.
Okay, understood. So the other question from Michael is that they're still curious about the pre-processing and they still want to know that in your training, any pre-processing in your P model or your RFD CNN model is for this different light condition, or you just use the different training pattern to capture the different light condition for your input training pattern to solve this issue.
Okay, so yes, we did add some noises to the training data, and it's like data augmentation, and we hope with this data augmentation, our model can deal with the noises. Yes, so we do train the model with some noise cases.
Okay, great, that's great. So I think that's all the questions from our audience, and thanks for your fantastic talk. Thank you.
Okay, thank you to our strategic partners who supported us, especially some of the key partners here. We've got ARM who help with hardware and software. The Tiny, what's called Edge Impulse for developers on the libraries. Qualcomm Advanced AI Research as well for their support in edge computing. Syntiant around hardware and ML training pipeline. So definitely thank you as well. Platinum sponsors, Reality AI for advanced sensing with product and TinyML. Renesas for microcontrollers and microcomputers. Our gold sponsor, Sladen.ai, Adaptive AI for the Intelligent Edge. Maxim Integrated, enabling edge intelligent devices. Seed Hardware, who also had present today. I'll quickly go back to them. Thank you once again for all your support. SensiML, build smart IoT sensor devices for data. SynthSets, and our silver sponsors. So thank you once again. It's been a great few days. Look forward to 2022, as mentioned before, and hopefully see you at some of the future Tiny ML events. Thank you.